Alright, hello. Here in this video we're going to be checking out the 2.4 notes, sketching graphs of functions. So the why for this is we use descriptions to visualize and make sense of information. When we read a book, we are able to visualize and create. When someone's describing a sporting event to you, you're able to kind of visualize that. Sometimes people will give you instructions such as, back before Google Maps, or if you're just walking somewhere, they might tell you where to turn, and then when you get to that intersection, what room you're looking for, and we're able to follow through on that, right? Based upon where we start, we're able to take different actions and figure out where we're supposed to go. With architecture and art design, when we're creating things, people give you a description of what they want, or they say, hey, we want a building and we want it to kind of have this sort of style, we want this many rooms in it. And they will create something like that for you. Or with art, you usually have a vision of what you're trying to create, and then you, using key features, make it happen on the page. So sketching graphs of functions is going to be us taking all sorts of information that they give us about the graph, and we're going to turn it into the picture that matches. So in order to sketch graphs of functions, you have to use the key components. And this vocabulary here is going to be a lot of those different key components. So we're going to write in the vocabulary words that match these, and then we'll later see these coming into play as we are sketching the graphs of functions. So this first one, the x-coordinate of a point where a graph crosses the x-axis, that's what we've been calling a zero. It's also known as an x-intercept. And then in a similar fashion, the y-coordinate of a point where the graph crosses the y-axis, this one doesn't have a special name like 0. It's just called the y-intercept. Oftentimes, though, it's thought of as your starting values, because the y variable describes kind of the starting component. So sometimes you'll hear it described as starting value, but it doesn't get a fancy name like 0. It's just y-intercept. So this third one describes where the graph's going at the end. We used arrows such as up, down, up, whatever. But this is talking about the end behavior. Ending behavior is going to be important to understand our graphs. Next one, a function that can be graphed with connected lines or connected smooth curves. Blue. So when we're sketching our graphs are going to be continuous. All right, so they're going to be nice, smooth curves. All right, then we have the maximum and minimum values of a function. Oh, yeah. So this is extrema. Extrema is the maximum and minimum values of a function. And we are looking at them from relative extrema because they're not necessarily going to be the ultimate maximum or minimum. Sometimes they will be. But sometimes they're just the tops and bottoms of the little curves that occur. We also call them the turning points. Turning points. So when a vertical line divides the graph of a function into two halves that are mirror images of one another, this one was line symmetry. So we have line symmetry. A function that has the graph of a straight line, this is linear. And a function that has a graph that is not a straight line, that's nonlinear. And that'll be important to know because if they tell you that a function is linear, it's very easy to sketch. We're just trying to find 2 points, right? Because it takes 2 points to make a line, and then we can draw it. If it's nonlinear, they can look like all sorts of stuff. We saw some that, maybe looked like that. Then we'll need a lot more information to make a nonlinear sketch. Alright, now as you all may have seen in the homework answer key, the textbook did ending behavior different than I had initially showed us in class, which I didn't address that the answer key would be doing that. But what we're going to see here is a description of what they were doing. Now I know that some people were able to figure it out, but they're going to do ending behavior different than we did. Now what we did for ending behavior was arrows. Like if we were looking at this function right here, we would have described its ending behavior as down and up. So the left and the right. The way that they're doing it is that same concept, except they're going to use kind of function notation to cover this. All right, now it's very easy to read. There's not too much to it. There's going to be two options. There's going to be as x approaches negative infinity and as x approaches infinity. Now, if you think about the x values here on the x-axis, right, which I'll put on here in red, when x approaches negative infinity, that's heading to the left. So whenever you see x is approaching negative infinity, that's talking about the arrow that would be on the left. So for us here in our example, if you take a look at our graph that I drew up there, the curvy one, as we head to the left, our arrow is pointing down. And so f of x, which really just stands for y, so it's asking, hey, what are the y values doing as x heads to the left? Well, if we look at the left bound of our function, it's pointing down, so this one is negative infinity. Our y values are pointing down, so it goes to negative infinity. Now, the second one, where it says as x approaches infinity, that's us heading to the right. So that's going to cover the right arrow. And if we look at our graph, this arrow here on the right is pointing up. So as we head to the right, our y values are facing up, so it heads to infinity. So those are the only options, are negative infinity, infinity. You're just deciding as it goes to the left, are you pointing down or up? And as you head to the right, are you pointing down or up? So this part will always be there for you. Like this is, you're only filling in two things. So if you're worried about it because it looks strange, they'd even give you this. They'd say as you're heading to the left, this is really the only value you're trying to fill in, is what's your y values doing. All right, and then they could give you one heading to positive infinity, and that's your right arrow. And then it's asking you, what are your y values doing? All right, so here we're going to start to use the key features to actually sketch some of our graphs. And we're going to start off with one that is linear, right? Which means we know we're going to be making a line, which so it'll be a little bit easier than a curve. So it says use the given key features to sketch a linear graph. So we know we're looking for a line. We just need a couple coordinate points to help make this happen. And they're going to give us some information to assist us. Okay, so it says the y-intercept is 3. That one's very straightforward. That means we have a y-intercept coordinate point right here on the y-axis of 3. All right, now the next part's tricky. It says the function is positive when x is greater than negative 3. That's actually describing an x-intercept. We're going to come back to that one. But let's talk about the ending behavior. It says the function is increasing for all values of x. That's some extra information here that's not actually describing end behavior. That's just telling us we have a positive slope. So we know our graph's going to have, it could have different steepnesses to it, but it will have positive slope. And if you draw out all the different renditions of positive slope, you can see that the ending behavior, from the way that we learned it last week, this ending behavior that they are describing here is going to be some type of rendition of down and up. All right, and you can see that on all these different drawings of positive slopes. The arrow on the left points down, the arrow on the right points up. So we know on our graph we're expecting a down and up, and we can see that in their rendition as well, because it says as x is heading to the right, because infinity is to the right, our y values are pointing up towards infinity. As x heads to the left, we are pointing down. Okay, so let's talk about the part there in green. This is a tricky way of describing an x-intercept to you. So I'm going to kind of help you visualize this a little bit better, because it says the function is positive. So a way that you could translate that is that it's talking about the function, which is y values. So we have positive y values. We have positive y values when x is greater than negative 3. All right, well, let's go ahead and plot the negative 3 and see how this makes sense. So here's the x value of negative 3. If you notice here that when x is negative 3, we're neither negative nor positive. when x is negative 3, we're at 0. All right? And then the opposite of that would be if we have x is less than negative 3, our y values would be negative. And when we take a look at this chart, I'm going to go ahead and draw in the line because we have our x-intercept and we have our y-intercept. So I'm going to go ahead and connect them with the line, put our ending behaviors on there. If we look at this concept of the negative 3, if I pick any values in terms of an x-coordinate that's greater than negative 3, let's pick negative 1. If I pick an x-coordinate of negative 1, notice that my y value is positive. However, if I pick an x value less than negative 3, such as negative 4, my y values are negative. So whenever they give you a description like that, where it says the function is positive for x is greater than negative 3, that x value they give you is going to be describing an x-intercept. So you don't necessarily have to understand this component. That's just them describing for you where the x-intercept is. All right. So let's take a look at these key features to sketch a nonlinear graph. Now, when it says nonlinear, what that means for us is our graph's going to have some curves and some relative maximums and minimums. It will not make a straight line like the one above. So let's go ahead and take a look. So it says the function is continuous. That's just telling us we're going to make it into a nice smooth curve. You know, it's not discrete data. And it says that we're symmetric about the line x is equal to negative 5. So what I'm going to do here is I'm going to bring in a dotted line, because that's typically how we do line symmetry. The equation x is equal to negative 5 is going to be a vertical line through negative 5. So this is a line of symmetry for us. That's going to be a reflection line, which means we could be getting some type of quadratic situation here, or any other type of function that is going to be symmetrical. All right, so we're going to come back to that to make sure that the function that we have graphed is can be reflected about that line. All right, so let's use some more information. It has a minimum at negative 5, negative 1. That's going to be right here. And then it says our ending behavior. As x heads to the right, we're pointing up. So I'm going to place a little up arrow on the right. As x heads to the left, we're also pointing up. So I'm going to put an arrow there. And you can kind of see now how this will be symmetric. And we're just sketching, so I don't need to know any of the other points. This curve ends up just looking like that. All right, is it symmetric through that dotted line? If I'd have done a better job drawing those, then it would have been. But that's kind of the concept. So if you wanted to make, a better sketch, you want to make sure that, you get a more symmetrical looking line out there, like that, because now it's a little more symmetric. And there's lots of different varieties of these. So you'll get to experience with all types of scenarios, both linear and nonlinear, using key functions. We'll cover this problem together at a separate time.